So question number 27 of our book related to the probability and random processes, and here we are asked that a number x is selected at random in the interval -1 to 1. Okay, so let us have the events. A is x is less than 0, B is the modulus of x minus 0.5 is less than 1, while the event C is x greater than 0.75. Okay, so we have to find their probabilities and the probabilities of their intersections. Okay, so initially, before starting the question, let us look at the events and the underlying concept here visually. Okay, so suppose we have this line. Okay, so this is the line, and here these are the axes. This is axis where this is 0, and here this is 1, this is +1, and this is -1. Okay, so the event A, let me denote it with red color. The event A, let me denote it with the red color, and here the event A is x less than 0. So what is that? This is, let me have this event, and it lies here. This is my event A, which is represented by this red color. Similarly, in order to represent the event B, what we have to do here, we can see that in event B 0.5 is subtracted from x, and the modulus of that value is less than 1. Okay, should be less than 1. So we can see here that in overall this area from 0 to +1, all the values basically satisfy this condition. So if I put 0 minus 0.5, so here it would be minus 0.5, while the modulus of it will be 0.5, which will be lesser than 1. Similarly, if I put the highest value here, which is 1, so 1 minus 0.5 is already less than 1. Okay, so let me represent it with what? Let me represent it with this green color. Okay, and in representing it with this green color, let me have it so this also satisfy this one. Okay, so I am representing it with this green color. So what about the others? So if I can see here that in the negative end, if I put -1 here, so it will be -1 minus 0.5, so it would be what? -1 minus 0.5 would be minus 1.5, and the modulus of it will be 1.5, which is greater than 1, which doesn't satisfy this condition. Okay, similarly, the half of it is how much? The half of it is minus 0.5. so minus 0.5 minus 0.5 is this, so I will get -1. so here I will get 1, which is equal to 1, so it also doesn't satisfy. So what we have to do? So as you can see that this is the continuous process here, so 0.49999 will basically satisfy this condition. So here if I will write 0.49999 and I will subtract 0.5 from it, I will get something here which will be less than 1. Okay, so this will satisfy it. So therefore here I will have, okay, so here I will have minus 0.5 and here it will satisfy this one. Okay, so it also lies here. So the green one is what? That is basically the event B. Similarly, in order to represent event C, let me use another color here, and that is the blue. So writing blue here, what I will have to do, let me represent it with this blue, and that is x greater than 0.75. so 0.75 almost lie here, so that is 0.75. okay, and here it will lie like it will be here, so that is the event C. So this is event C with green, this is event B, while in red this is event A. Okay, so I hope the overall scenario will be clear now. Okay, so what we have to do now, let me solve it, and before solving it, let me clear this screen. Okay, so I have to find the probabilities of each and every element here. So I can see that the probability of A will be, as this is basically the line function, so distance between 2 points of A, okay, divided by the total distance. Okay, so the total distance here is how much? So let me write the formula here first. Okay, so in A we can see that it lies from 0 to 1. So here the distance here would be from 0 to minus 1. So the area here will be 0 minus 1, okay, divided by what? Here the area is 1 minus 1. So it would be 1 divided by 2. Okay, so here the probability of A is 0.5. Similarly, the probability of B is how much? Using the same formula, that distance between 2 points of B now divided by the total distance. So the total distance will remain same because that is 2, while the probability or the distance between 2 points of B are how much? So it can be here like 1 minus 0.5 will be how much? So it would be 1 minus 0.5. okay, so how much would it be? That would be 1 plus 0.5 divided by 2. So it would be 1.5 divided by 2. How much would it be? So let me calculate it. 1.5 divided by 2 will be 3 by 4 or 0.75. So the probability of B is 0.5, while the probability of C is, again using the same formula, while the distance here is 1 minus 0.75 divided by 2. So here I will have 0.25 divided by 2. So here I will have how much? 0.25 divided by 2 will be 1 by 8 or 0.125. So these are basically the probabilities of A, B and C. Okay, so these are the events and I have already found out their probabilities, which are here, while this one is for the A, this is for B. I am using the same colors which I have used here, and this one is for the blue. Okay, now finding the probabilities of A intersection B, what I have to do, here first of all I have to see that what is A intersection B, the area where A and B are intersecting each other. So this is basically the area. We can see that this is the area where A and B are intersecting each other, and that is basically 0.5. So that area is 0.5. okay, so in order to find the probability of A intersection of B, I have to write the 0.5 divided by the total distance here. So here it would be 1 by 4, or how much would it be? 0.25. So the probability of intersection is 0.25, and this is this one area. So let me write here as well, this is A intersection B. Now in order to find the probability of A intersection C, so what is A intersection C? So this is A, this is C, so there is no intersection between them, so therefore it will be 0, and in order to find the probability here, it would be divided by 0, so the probability of it is 0. okay, so the probability of A intersection C is 0. So that's it for today, in which we have discussed this problem, and I will see you with some more problems in our upcoming videos. Thank you. Hi again. So today we are going to discuss some important problems which are related to the probability and random processes for electrical engineering second edition. So the first problem here is basically the 32nd problem, and what is it asking us to find the combination to a log is given by 3 numbers from the set 0 to 59. Find the number of combination possible. So here we can very easily see that there are basically three, we have to pick the three numbers, and we have to see that how many combinations are possible if we pick three numbers from these 60 numbers. Okay, so again, let us suppose we have here three spaces, and in each of these three spaces, how many possible choices do I have? So in the first space I have 60 choices. Okay, in the second space, how many choices do I have now? Because repetition is allowed and it is the sampling with replacement, so now again I have 60, and at the end I have again 60. So these are the three spaces, and here the number of choices will be 60 multiplied by 60 multiplied by 60, and that is basically the 60 raised power 3. So the number of possible combinations are basically 60 raised power 3. So these are the number of possible combinations. Okay, so that is the answer. Similarly, in another problem, it is asking us to find the number of possible outcomes for a six-sided dice tossed, a coin is flipped, and a card is selected at random from a deck of 52 distinct cards. Okay, so we have to find the number of possible outcomes. So here we can very easily see that this is basically the AND problem, in which the die is tossed and a coin is flipped and a card is selected at random from the 52 distinct cards. Okay, so this is the AND problem, and for all the AND problems I basically use the multiplication here. So for the 6 possible outcomes here, similarly the 2 possible outcomes for the coin toss here, and the 52 possible cards here, this is the outcome. These are the possible numbers of outcomes. So the answer here will be 624. Okay, so the 624 number of possible outcomes are available here. But what is basically the concept here? The concept here is basically the multiplication rule, that what are the situations where I can use the multiplication. Similarly, if there was the OR situation here, if there would have been the OR situation here, I would have used the addition sum here instead of this multiplication sign. Okay, so now the basic concept here is to see the applicability of multiplication and addition here. Okay, similarly in problem 34, a student has 4 pair of shoes and never wears the same on 2 consecutive days. In how many ways can he wear shoes in 5 days? Okay, so basically he has 4 pair of shoes, 4 pairs he has, and let me write those pairs like 1, 2, 3 and 4. Okay, these are the pair of shoes he has to wear, but in 5 days he doesn't repeat the pair in the consecutive days. Okay, so let me again use the same concept which I have used for the problem 32. So writing the number of days here like 1, 2, 3, 4 and 5. Okay, so in the first day, how many choices do he have? He have the full choices, and he will have these 4 choices. Okay, the 4 choices out of 4, he has to pick one of the pair of shoes which he has to wear on that day. Similarly, after it, the day after it, he will not use the same pair of shoes he has worn in the previous day. So therefore the number of choices he would have would be 3. Similarly, on the other day, he again can use the pair of shoes which he worn on the day before a day, but he cannot wear shoes now which he has day before it. So therefore again 3 choices. Similarly here and here is as well. So as you can see that this is again the combinatorial problem. So I will use 4 multiplied by 3 multiplied by 3 multiplied by 3 multiplied by 3. So that would be 3 raised power 4. I will have here 4 multiplied by 81. So that would be 324. Okay, so he would have 324 choices, out of which he can use any one in the 5 days week. Okay, so that is the solution of this problem. In problem number 35, he is asking us to find the 7 digital telephone numbers are possible if the first number is not allowed to be 0 or 1. Okay, so we have to find the possible number of 7 digit telephone numbers in which 0 or 1 is not allowed in the first place. Okay, so again I can use the same concept. This box type concept is a very useful thing which will enable you to solve the very complex problems. So grasping the conceptual overview of this is very important for you. So again, now dividing into the 7 possible slots, 1 2 3 4 5 6 and 7, 1 2 3 4 5 6 7. Okay, so now initially in the first place, actually how many numbers do I have? I will have 0 to 9, 10 numbers or 10 digits here, but initially in the first place he will not include 0 or 1 here. So 2 will be left here, so I will have 8 choices here. 8. How many choices do I have in the second place? 10. In the third place again 10, fourth place 10, and 10 here, 10 here, and 10 here. Okay, so again this is a combinatorial problem. So 8 multiplied by 10 raised to power 6 basically is the answer here. Okay, so that is the solution of this problem, in which the allowed number of the telephone numbers will be 8 into 10 raised to power 6. So this is again one of the combinatorial problem. Let's move on. Okay, so in question 36, ordering a deluxe pizza means you have 4 choices from 15 available toppings. So the available toppings are 15, and out of these 15 you have 4 choices. How many combinations are possible if toppings can be repeated, if cannot be repeated? If the number of toppings can be repeated or if cannot be repeated. So let us first solve the problem where toppings can be repeated. Okay, so if the toppings can be repeated, so how many choices of the toppings do I have? Again I have 4 choices here, so 4 slots here. So in the first slot how many choices do I have? Again 15. In the second again 15, 15, and at the end again 15. So how many possible choices do I have, or combinations do I have? Those would be the 15 multiplied by 15 multiplied by 15 and multiplied by 15. So it would be the 15 10 raised to power 4. Okay, so these are the total number of choices if the toppings can be repeated. Similarly, the second part of this, in which it is asking us that the toppings cannot be repeated, so no repetition is allowed. No repetition is allowed. So again using the same diagram or the same slot concept here, so 1 2 3 and 4. So initially in the first place, how many choices would I have? I will have 15 choices, then I will have 14 choices, then 13, and then at the end I will have the 12 choices. Okay, so here how many numbers can I have? I will have 15 multiplied by 14 multiplied by 13 multiplied by 12. Okay, so getting the product here, I will get the answer, or from it I can also use the concept of the permutation, in which I have to use the NPR, where the N is 5 and R is 4, and from it I will get the, let me write it here, I will get the 15 factorial divided by 15 minus 4 or factorial, and from it I will again get the same combination or the same number here. So that is the solution where the toppings cannot be repeated. Okay, so that is the solution of problem 36. In 37, I have to find that in how many ways 10 students can occupy 10 desks, and similarly the same number of students can occupy 12 desks. Okay, so let me repeat it for the 10 desks. Using it for the 10 desks, again I can see that I will have 10 slots, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So there are basically the 10 desks. So initially for the first seat I will have 10 choices, and for the second I will have 9, then 8, 7, 6, 5, 4, 3, 2, 1. Okay, so these are basically the choices that initially for the first seat I will have total 10 number of students, and any one of those 10 students can occupy this seat. Similarly, when one of the 10 students will occupy this seat, now 9 students are remaining, and one of those 9 students will occupy the second seat here. Similarly, when out of 9, one of the students will occupy the second seat, again the number of choices I will have 8, then 7, and repeatedly one of those choices will be decreased, and at the end I will get one student which will have the only choice is to occupy the last seat which he has. Okay, so this is basically the problem, and this is the 10 factorial here, that 10 students have to occupy the 10 seats. Okay, similarly in B, where 10 students has to occupy the 10 desks. So this is basically the permutation problem, in which the number of desks are basically 12 and R is here 10. So NPR is basically NPR is 12P10. So 12 factorial divided by 12 minus 10 factorial, or 12 factorial divided by 2 factorial. So these are the number of choices that these number of students can occupy the 12 desks in my question. Okay, so that is the solution of the question number 37. In 38, it is asking us that a toddler pulls 3 volumes of an encyclopedia from his shelf, and after being scolded, place them back in a random order. Okay, what is the probability that the books are in the correct order? So initially the books were in some order, a toddler pulls them out, and then after another person scolded him, he puts it back, and we have to find that what is the chance that when he put back those encyclopedia, those were in the correct order. Okay, so again let me use the same diagram here. Okay, so here how many possible choices will he have to put the encyclopedia in the shelf? So initially how many books for the first slot he has? He will have 3 choices. For the second slot he will have 2 choices, and for the last one he has 1. Okay, so by seeing it I can very easily see that is a combinatorial problem. So 3 multiplied by 2 multiplied by 1, this is 6, and also this is basically the 3 factorial problem. So he has 6 number of choices in which he can put those encyclopedia, or 6 number of orders are basically the number of the orders of the 3 encyclopedia books which he can put on the shelf. Okay, so out of these 6, just 1 order is the correct one, so therefore the probability of it will be 1 over 6. So this is the probability that a person will put back the encyclopedia in the correct order. Okay, so that is the answer of my question 38. Now in 39 problem, what is it asking us? A deck of cards contain 10 red cards numbered 1 to 10 and 10 black cards numbered 1 to 10 as well. How many ways are there of arranging the 20 cards in a row? This is the first question, and let me solve it first. So as he has 10 red cards and 10 black cards. Okay, so these are basically 10 plus 10, 20. So the total number of cards are 20. So initially, now again considering the 20 slots here. Okay, so these are basically the slots. I'm writing it like this because the number of slots are greater than the available space with me. So initially he will have 20 choices, then 19, then 18, then 17, and at the end he will have the last choice. So as it is the combinatorial problem, so multiplying them together I will get the same numbers here, and this will be the 20 factorial number of choices in which he can arrange 10 red and 10 black cards, okay, which are numbered from 1 to 10. This is the answer of the first part. Similarly, in the second part, suppose we draw the cards at random and lay them in a row. Okay, so what is the probability that the red and the black cards alternate? So this is somehow a trickier question in which we have to see the concept behind it. So again, let me have this slot here. So the number of slots here are again 20. So 20 number of slots are available here, in which initially if I consider the 10 red balls and 10 red cards and 10 black cards. So if the first card here is the red one, so the second one should be the black one, the third one should be the red, the fourth one should be the black one, and so on. So initially the choices for the red will be 10. Okay, so after it I have to put here the black one, so the choices here for the black are again 10. Again, now as one of the 10 red cards is placed here, so in the third place I have now 9 choices for the red card, and for the black card here I have the 9 choices as well. So at the end what I will get? I will get the choices like 10 into 10 into 9 into 9 up to 1 into 1. Okay, so how it would be? It will be 10 factorial multiplied by 10 factorial or 10 factorial square. So this is basically the choices for the initially red and then black as well. So there is also another possibility that I can also have the black card at the first as the first card, and then the red one, and then red, and then black, then red one. So initially I will have here the black one. So that is another possibility. For that possibility again I have the same combinations and the same possible number of outcomes here. So I will get here 10 factorial whole square here again. So that is again another possibility. So in order to copy it here, let me move down here. These are basically the 10 factorial, this one. So the choices I will have will be either, let me move it, either the first red choices or the first black choices. So these are basically the two choices, and any one of those will be here, can be here, which is the possible outcome. So tackle the questions where or is concerned, or one of the two will be the correct one. I can use the plus sign here, and that is basically used to denote the or operation. Okay, so here for first red choices, how many combinations will I have? I will have 10 factorial whole square, and similarly for the first black I will have 10 factorial whole square as well, and here it will be 10 factorial whole square. Okay, so that is the choice when the red and black will alternate with each other, and the total number of choices I have is how much? So the total number of choices I have is basically 20 factorial. Okay, so now in order to find the probability of the alternating cards, what will happen? I have to write here the number of choices when I will have the alternating cards divided by the total number of choices which I have. So that is the answer of this question. where when I have the alternating number of red and black cards. Okay, so that is the solution of my problem. So because of the limited space, I basically move down here, but the choices or the question here as well the same one. So that's it for today, in which I have discussed many questions which are related to the probability and random variable, and with some more questions I will get back very soon. Till then, take care of yourself, and I will see you very soon. Thank you. Hello guys, so this is another very important and very interesting question, where in this computer network scenario we are asked that in how many ways a packet which is started from here may reach from NS to this ND, that is the output node here. So we have to find out all the possible ways from which this can reach here at N of D. Okay, so this is clearly the combinatorial problem, and we can solve it very easily, but here we have these intermediate nodes which can be tricky to handle, and these can be very confusing here, but this question can be solved in many ways. But the first and the foremost method here is this one. So suppose a packet is here. Okay, so we have a packet here, and in order to select the path from these three, what it has to do here, he will have basically three choices. Okay, so out of these three choices he will have to find any one of them. Okay, so after it, when it will reach here, so how many choices will it have here? So when it will reach here, he will have one choice to reach this N4. Similarly, this another choice, let me draw it with this red, this another choice from N1 to N2 to reach N5, and similarly this choice with which it will reach from N1 to N6. Okay, so these are basically the three choices when it will reach here. Similarly here for N2, let me denote it with this blue. Here for N2 it will have this choice one, similarly this choice and this choice, so it will again have three choices. And similarly this third one, it will have this choice, let me draw it with green one, so it will have this choice, similarly this one, and the last one is here. So again at any point here it will again have three choices. So here three again, and here at this third layer it will again have three choices to reach here. Okay, so these will be 3 3 3. Okay, so now we can see that these will be 3 in each layer, but what we have to do, either we have to write plus plus here, or we have to write multiplication here. Okay, so which sign to use here? It is a bit confusing that which sign do we have to use here. So we can see that whenever this node will select any of the path here, it will also select the other path from that node as well. Okay, so this will be clearly the AND problem. Okay, so let me call it L1 and this L2 and this is L3. So clearly when it will come here, it will select L1 and L2 and L3. It's not possible that it will select L1 or L2 or L3. Okay, so this will clearly be the process where he will have to select any of these paths. Okay, so as it has to select all the paths, or he will have all the options here, here and here and here. So here this is the AND problem, and I have previously told you that for all the AND problem I have to multiply, and for all the OR problems I have to add the digits. Okay, so now here as this is clearly AND problem, so I have to use this multiplication. So it will be 3 raised to power 3 and it will be 27. Okay, so here we have 27 number of different paths here. So many people may find it very confusing because they may see it like this one. And here they can see that this is at this point it will have this choice, similarly here it will have this choice and this choice, but they are not going to encounter it. Similarly at that condition they might have 3 plus 12 plus 12, which again will give you 27 paths, and due to those paths it will be 3 plus 2 here, this one and this one, multiplied by the 3 paths of this n2, which are this one and this one, okay, and 2 parts of it, which are these one, okay. So these are again 2. Similarly for this one as well, and here they will get 27, but here this plus sign will be confusing because of our formulated scenario, okay. So this type of questions can also be modeled like this and this. Similarly here this node, this node, this node, and last one here. So in order to draw it, what will happen, this is the first one, then this one, then this. Here it will get here or here or here. Similarly here as well it will have again 3 connections, and here it will again have 3 connections, and last one here, okay. So it is clearly be seen here that if this is n of s and this is n of d, so here at each step we have 3 and 3 choices, and again the same formulation we will get. But what was confusing here, so the only confusing thing here which we have seen was due to the availability of these intermediate nodes, okay. But the problem here is just like this one, and if we just concentrate over the destination from here to this second layer, this type of questions will be easier to solve, okay. So this is about the problem of this computer network type packets destinations and all the paths. In different applications we also have to find the optimal path which will give us the lowest losses, and similarly the shortest path from the ns to nd, okay. So in those type of questions, these type of scenarios are quite often to encounter, okay. So that's it for today, and I will see you with some more stuff which is related to the probability and random variables in our upcoming videos. Thank you so much, and I will see you soon. Hello again. So this is the question number 2.43 in the book of Probability and Random Processes for Electrical Engineering by Alberto Leon-Garcia, and this is the 3rd edition of that book. In that book I have found this question which I have seen as one of the most important questions in learning how to crack different passwords, and have been used in many years by many practitioners to crack the passwords, okay. Similar manner you also use in your daily life to crack different passwords or different passcodes of different doors or boxes, okay. So what it is asking us to find, so a website requires that users create a password with the following specifications, and the password length ranges from 8 to 10 characters. It also includes one of the special characters which are given here. These are basically 1 2 3 4 5 6 7 8 9 10 11 12 13 14. These are basically the 24 characters, okay. Special characters are 24. No spaces, it shouldn't have any space in between any character. It may also contain numbers from 0 to 9, lower and uppercase letters A to Z, which are basically 26, and separately 26 here because this is the case sensitive, okay. So what is it asking us to find, that how many passwords are there. If you can use the password length from 8 to 10 characters, in which you must have include the character or the special character out of these 24 characters. So how many passwords can you get, and how long would it take to try all passwords if a password can be tested in 1 microsecond. 1 microsecond, and this 1 microsecond is 1 into 10 raised power minus 6 seconds, okay. So now let me use this green color for solving this question here. In solving it, what we have, basically we have let me consider again this block here, and it will be composed of 9 slots. Okay, in these 9 slots I should have, basically in the first slot I should have one of these 24 characters. In the second slot I should also have one of these 24 characters, and up to the nth slot here I should have the one of the 24 characters as well. Okay, so either this will have one of these characters, or this one, or this one, or this one. So this is the basic condition for any password to be valid, is that one of these 24 characters should also be here. Okay, so if all the others are available and none of these 24 characters is available, so that password will be non-valid. Okay, if none of the 24 characters are available. So what would we do? This is the OR condition, so we should write plus with all these 24 or these choices. So what will happen? 24 plus 24 plus 24 up to the 24th element here. So it will basically be n multiplied by 24 or 24n. Okay, so that is the basic condition for my passwords to contain the special characters here. Okay, so that is the first rule, and let me call it equation 1. Okay, after it let me have now again, so for condition number 2, one of the n slots has been captured by the special character. So how many slots now are left? So n minus 1 are left now. Okay, so out of these n slots now how many slots are left? N minus none, n minus 1 slot. So how many characters can basically occupy those spaces? So in these n minus 1 I can also use the 24 special characters, because it is already given that at least one special character should be included. So more than one can also be included here. Similarly, the 26 small alphabets can also be here. So 26 here. Similarly, 26 uppercase letters can also be included here, and similarly the numbers from 0 to 9 can also be included here. Okay, so how much is it? It will be 26, 26, 52, 52, 10 is the 62, 62 plus 24 is 86. So I can have 86 characters. Okay, so in these n minus 1 slots, okay, as I have now n minus 1 slot, in each slot how many possibilities of the characters will I have? Here 86, here 86, here 86, and up to this one. Okay, so this is also the sampling with the replacement task, in where any of the 86 character can be used here, and so on for each and every slot here. Okay, so how many characters would I have here? So this is basically the AND condition, because all the n minus 1 slot has to be occupied. So that's why these would be 86 multiplied by 86 multiplied by 86 up to the 86th n minus 1 character. So how many elements would I have here? I will have 86 n minus 1 choices here. Okay, so now the basic condition is here for the for the nth character, and this is for the n minus 1 characters. What would happen now? Here let me use the black color here again. So here with this 24 n into 86 n minus 1, I will have passwords for n characters. Okay, so that is the password for the nth number of characters, and similarly here I have the minimum length of the password is 8 and the maximum is 10. Okay, so let me write it for the all possible lengths. Okay, so the possible lengths can be 8, n is equal to the 8 plus n is equal to the 9 plus n is equal to the 10. Okay, why am I using plus here? Because any of these three can be used here. It can be 8 or 9 or 10 as well. Okay, so now putting the values here, what I will get here, I will get here 24 into 8 into 86 raised to power 7 now, plus 24 multiplied by 9 multiplied by 86 raised to power 8 now, plus 24 multiplied by 10 multiplied by 86 raised to power 9. Okay, so what will be the answer here? And by calculating it, I will get 6.24 into 10 raised to power 19 passwords. So these are the total number of passwords which I will obtain from the conditions which are given here. Okay, so these are basically the passwords which are given from the conditions mentioned here. Okay, so what is the next step? In next step we have to find out that how long would it take to try all password. Is a password can be tested in 1 microsecond. Okay, so these are basically the passwords here, and in B here, time to crack all passwords is equal to that is basically the total time. So time for one password multiplied by the total number of passwords. Okay, so the time for one password is 1 microsecond, that is 1 into 10 to the power minus 6 multiplied by 6.24 into 10 to the power 19, and now using it I will get 6.24 into 10 to the power 13 seconds here. Okay, and converting it into the years here. Okay, what would I do? I would do 6.24 divided by the in 365 days, in each day I have 24 hours, in 1 hour I have 60 minutes, and in 1 minute I have 60 seconds. Okay, so 6.24 10 to the power 19, and from by solving it from this one, what I will get? I will get the 2 into 10 to the power 6 years. Okay, so this is the time required to crack all the passwords, and this type of technique in which I have to follow all the number of passwords is called the brute force algorithm, in which I will follow through all the passwords unless and until I will get the password which I need. Okay, so that is the question which I found very important for you to grasp the concept of, and that's why I have solved it alone and did not mix it with other question like I have solved the previous questions. Okay, so I think it's enough for today. You have grasped the concept which is necessary to solve these kind of questions. Welcome back, guys. So this is question 43 of our book, which is Probability and Random Processes by Alberto Leon-Garcia, and the edition we have is the second edition. So what is the question here? So you win a lottery ticket if you correctly predict the numbers of 6 balls drawn from an urn containing balls numbered 1 to 49. Okay, so all the numbers, there are basically 49 balls, and the numbers written over those balls are from 1 to 49. So this basically sampling is without replacement and without regard to the ordering. So whatever order you will have, if you predict that correctly, you will win the lottery ticket. So how many possible orders are there? So here inside this urn, so suppose we have this urn, and here we have different balls, okay, and over each balls there are written some numbers from 1 to 49. So basically we have how many numbers here? So in sample space we have numbers from 1 to 49. So there are basically 49 balls here. So a person has to pick 6 balls from it, and he has to predict the numbers correctly in order to win the ticket. So how many ways can he pick the balls from here, so that there is no replacement and no ordering here? So this is clearly the question of the combinations. So the combinations here are basically NCR. The N here is basically 49, R is here 6. So how many NCR are here? So 49 factorial divided by 49 minus 6 whole factorial and multiplied by 6 factorial. Okay, so this would be the equation here. So now writing it, 49 multiplied by 48 multiplied by 47, okay, 46, 45, 44 and then 43 factorial. Why did I write it like this? It will be clear in a while. So 49 minus 6 is 43 factorial, and it will be multiplied with the 6 factorial. So these two will cancel out, and at the end these things will remain here. So 6 factorial is basically how much? Writing it here, so 6 factorial is, where is the factorial here? That is, so 6 factorial is 720. Okay, so that is the 720. Let me multiply these terms. So 49 multiplied by 48 multiplied by 47 multiplied by 46. There are also other very feasible and easier methods for calculating it, but I am doing all these steps in order to clarify it to you that how these systems and these things work. So 46 multiplied by 45 multiplied by 44. Okay, so the answer it will have will be this one, and dividing it over 720, what I will get? I will get this number. So there are basically these number of possibilities here, and you will clearly see that this is now how much? 13, 98, 38, 16. Okay, so this is a quite huge number. I am not going to write it here, but this is basically very quite huge number, and any one of these combinations will be the answer here. So you can very easily see that the probability of predicting the number or predicting the sequence of the 6 balls is very low. So the probability of winning a lottery is also very low. Okay, so these type of tactics are used in the lottery winning systems and in gambles, where the predicting any numbers or any sequence of numbers is very hard, and it will give the ultimate advantage to the bar or to the casino where that game has been played. Okay, so this is about our question number 1. Similarly, in question number 2 here, what is it asking us? That find the probability the sum of the three tosses of a die is 7. Okay, so if in order to calculate it, what we have to do, first of all we have to write all the sequences which are available in the sample space. So as we are basically tossing the die 3 times, so writing all the combinations here will be quite hard. Therefore what I'm writing here, so how many items will I have, or how many sequences will I have in the sample space. So initially I have 6 choices in the first place, similarly 6 choices in the second place, and in the third place I also have 6 choices. So this is basically 6 raised to power 3. Okay, so in sample space I have these number of items here. Okay, so we have to find the probability that the sum of the outcomes of 3 tosses of a die is 7. Okay, so what is that? Let me call it that equal to A, and what would be those items? So that those can be 1 and 6. Okay, similarly 2 and 5, 3 4, 4 3. Okay, these are the items, and you can see that the summation of each of these terms is giving me 7 4 3. And similarly here we will have 5 2, and at the end we will have 6 1. Okay, so these are basically the number of items here. So how many items do I have here in A? So these are 1 2 3 4 5 6. So the number of items in A are basically 1 2 3 4 5 6. These are 6. So what is the probability of sum of 3 tosses is 7. So probability of A is that would be the number of items in A divided by the total number of items in the sample space. So the number of items in A are basically 6, and the number of items in the sample space are 6 raised to power 3. So these are 6 raised to power 3, and ultimately I will get 6 raised to power 2, or this is 1 over 36. Okay, so that is the probability that the outcome of the 3 tosses of a die is 7. Okay, so with this question I am leaving you practice over all this stuff, and I will see you with some more question in our upcoming video. Thank you so much. Hello students, so I hope all of you will be fine. Today we are going to discuss some more problems which are related to the probability and random variables, and that is the third edition of our book, that is the book by the Alberto Leon-Garcia. Okay, so the question 2.44 here is that a multiple choice test has 10 questions with 3 choices each. How many ways are there to answer the test, and what is the probability that 2 papers have the same answer? Okay, so first of all let us first find the answer of our first part here. So if there are 10 questions and each question has 3 choices, so how many ways are there to answer the test? Okay, so again we will try to solve it by using the same procedure which we have followed in our previous question, and in that procedure let us have this box here, in which let us have how many questions we have. We have 10 questions, so again we have 10 slots here. Okay, and that is it 1 2 3 up to this 10. Okay, so in first question, how many choices do I have? I will have 3 choices. In second question, how many choices do I have? I will have again 3 choices, then 3, and up to this I will have 3 choices. Okay, so what will it give us? It will give me that 3 and 3 and 3 and 3 up to the 10th 3. So it will give me 3 raised to power 10. Okay, so finding the answer of it will give me the number of choices, the total number of choices. Okay, so in this question the answer of part first is 3 raised to power 10. Okay, in part 2 it is asking us that what is the probability that 2 papers have the same answer. So in order to find it, let us find the probability of the answer that one person has got. So the probability of or any one answer, this one first person has got. Similarly, the same question when attempted by the other person and has obtained the same answer which the first has got is this one. So now if it has the same question as that of the second person, so it is the AND problem. So ANDing it here, I will get the probability that two papers have the same answer, and similarly multiplying them together I will get 320. Okay, so that is the answer of my question, and in this question you can clearly see the practical example of this AND here. Okay, so in previous question I have also told you that all the scenarios or all the conceptual procedures which we have been following here are due to either the multiplication procedure or this AND procedure. This multiplication is for the procedures where we will follow the and this is for the OR. Okay, so one of that procedure is followed here, and in previous question we have also seen the practical implementation of this OR as well. Okay, so that is the question number 2.44. Now in 2.47 it is asking us that a lecture room has 60 seats. In how many ways can 45 students occupy the seats in the room? Okay, so that is a very easy question, and that is basically the permutation questions, because if the order of the persons also matter here. Okay, so we have the formula NPR. So writing the NPR here, there are 60 seats, and 60 seats he has to occupy the 45 seats. So here it will be 60 factorial divided by 60 minus 45 whole factorial, or it will be 60 factorial divided by the 15 factorial. Okay, so that is the answer of this question, and similarly we can also answer the same questions in the similar way. Okay, so that is the answer of this question. Now let us proceed. Okay, so now we have another question here, and in this question it is asking us that 5 balls are placed at random in 5 buckets. What is the probability that each bucket has a ball? Okay, so suppose we have, again let us use the same example here. We have there 5 buckets. Okay, these are 1 2 3 4 5, and these are, let me, the first bucket is here, the second is here, third is here, fourth is here, and this is the fifth one. Okay, so these are placed in such a manner that it can also have more than one balls. So we have these balls. Okay, so 5 balls are placed at random in 5 buckets. Okay, so what is the chance that each and every one will have some combinations here? So initially in how many ways it can get the balls, or how many balls it can get? It can get 5 balls. Similarly, it can also get 5 balls, it can also get 5 balls, it can also, and it can also as well. So that's why this is the AND operation, in which each and every bucket has the choices of 5 balls. Okay, because I have told you earlier that each bucket can basically have the 5 balls as well. So here the total choices here will be, so the total choices here will be 5 into 10 raised to power, how much is this? This is 5 raised to power 5. Okay, so that is the total choices. Similarly, now if I want each and every one of these to have only one ball here, so initially in this bucket, how many choice will I have? I will have 5 choices. Then the first bucket will have 5 choices, and if it will have one ball has fallen into this bucket, how many choices will be left? So there will be 4 for the second bucket. Now again the one will be aimed at this bucket, so the 3 will be left, then 2, and then 1. So that is basically the 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1, and that is the 5 factorial choices. Okay, if each and every bucket has one ball. Okay, so what is the probability that each bucket has a ball? So that will be probability that each bucket has a single ball. So that is the permutations or the combinations when each and every bucket has one ball divided by the total number of possibilities or choices here. So that is 5 factorial divided by 5 raised to the power 5. Okay, so that is the problem 2.50, and I think it's enough for today. We will talk about more problems like this one in our upcoming videos. So today we also talked about all the previous concepts which we earlier on discussed here. So that's it for today, and I'll see you with some more examples very soon. Thank you so much. Hello guys, so this is question number 44 of the second edition of probability and random processes for electrical engineering by Alberto Leon-Garcia. So in this question we are asked to find the distinct permutations of 4 red balls, 2 white balls and 3 black balls. Okay, so what is basically the scenario here? So let us have here the urn, okay, in which we have 4 red balls. Okay, so how many red balls do we have? 1, 2, 3 and 4. Okay, these are 4 red balls. Okay, 2 white balls, we have 2 white balls. So writing white balls like this is the first white ball, while this is the second white ball, and 3 black balls. Okay, so black balls here will be, this is 1, 2 and 3. Okay, so this is the first black ball, this is a second, and this is a third black ball. So we have to find out the number of distinct permutations which we can get when we try to get each and every one out of this box. Okay, so we can get the black, red, red, black, black, red, red, white, white, similarly red, white, red, black, black and so on. So those all will be the distinct permutations which we can get out of these balls. Okay, so how many number of balls do we have here? So total number of balls we have here are basically 9, and out of these 9 balls the number of white balls are 2, the number of red balls are 4, or let me write them with the red as well. So number of red balls are 4 and number of white balls, so writing this white balls with this one, balls, and black balls are 3. Okay, so these are the things here. So in order to solve it, what we have to do, we have to use here the multinomial permutations. So in multinomial permutations, what we will have here, so in order to find the distinct component permutations here, we have to write here n factorial and divide it over the number of white balls and their permutations, number of red balls, their permutations, and number of black balls and their permutations. Okay, so writing them here, writing the values here. So 9 factorial divided by the 2 factorial multiplied by the 4 factorial and then 3 factorial. So what will be the answer? So in order to find the answer here, let me go to the calculator and here writing this 9 factorial. Okay, this 9 factorial divided by the 2 factorial multiplied by 4 factorial and multiplied by this 3 factorial. Okay, so now calculating it and I will get 1260. So 1260 is the answer. So I will have 1260 number of distinct permutations which will be in the sample space if I want to get all the balls out of this urn, and those will be the sequences in which I can get them randomly from this urn. So that is about the question which we have discussed now. We can also solve many questions like this one, that if in a house we have different kind of people like 2 childs, 4 males and 3 females, and if the people are going to get out the home, so what will be or how many sequences will we get if all of them will come out of their home. Okay, so the same type of questions will be solved like this one which we have solved today, and there can be many other possibilities as well, but one of the easiest example was given in this question which we have solved, and it will be the formulation for other type of problems which we may encounter in our daily life. So thank you so much, and I will see you with some more interesting questions related to the probability and random processes in our upcoming videos. Thank you so much. Take care of yourself. Welcome back, guys. So another very important and very interesting question today we are going to solve. So here in this question the statement is, consider a group of 20 people. Okay, so we have 20 people, and if everyone shakes hand with everyone else, so how many handshakes take place? Okay, so here in this question we are having 20 people in a group or in a home or in a room. So if every one of the 20 people shakes hand with everyone else, so how many handshakes in total will take place? Okay, so before going to solve this question, we are going to formulate the strategy which will give us the conceptual perspective of these type of questions. Okay, so suppose if we have some people here, let us have 4 people and 1 2 3 4. Okay, so if every one of these people shake hands with everyone else here, so how many handshakes will take place? So initially let us call this 1 2 3 4. Okay, so first of all this person will come here, okay, and he will shake hands with everyone here. Okay, so he will shake hand with this one, this will be the one combination. Okay, similarly here with this one and with this one as well. Okay, so we will have 3 handshakes. So once he will shake hands with all of these people, he will be eliminated, and after it what will happen, this person will get back here. Okay, so this is the second person, and he will now shake hands with third and fourth. Okay, so you again can see that here again we are having these two combinations. Okay, every time out of these 4 we are having a combination of 2 where the order doesn't matter. Okay, so suppose if one is shaking hand with 2, it is also equivalent to the 2 shaking hand with 1. Okay, so in these type of questions we can see that here we have 4 people, and at every instance we are going to select any 2 of the people here, just like here this 2 and 1. Okay, then let me use this color here. Okay, let me use this green color here. So first this 2 will make the combination with first, then this third will make combination with 1, and then 4 will make this combination. Okay, so it will giving us the perspective of this 2 persons out of 4, their different combinations in which order doesn't matter. Okay, so which type of question is this? So this is clearly the combinatorial problem. Okay, where we have NCR. Okay, so here if we have n equal to 20, okay, so R will already be equal to 2, because I have earlier told you guys that during the handshake 2 people will get back to each other. So therefore I am taking this r equal to 2. Now getting back to this question here, what I will get, this is, let me call this is any number of people here, but during the handshake or during a hug there will be two people in contact. Okay, so therefore in this formula it will be n factorial divided by n minus 2 whole factorial multiplied by 2 factorial. Okay, now simplifying it some more, what I will get, nc2, so it will be n minus 1 n minus 2 whole factorial divided by the n minus 2 factorial, and 2 factorial is 2. Okay, now these two will cancel out, and at the end what we will get, nc2 is equal to the n minus 1 whole divided by 2. Okay, so that is the formula which will be used for these type of questions, just like the handshakes or hugs, etc., for in certain group of people. Okay, so here now putting the values, so let me put values here. Here now when n is 20, what will happen, this will be 20 C2. So due to the formula here I will have 20 multiplied by 19 divided by 2, so this will be equal to 210 and it will be equal to 190. Okay, so there will be 190 handshakes when people in the room will be 20. Okay, and each and everyone else is going to shake hand with the other people. Similarly, this is the generalized formula which we have derived here, and it is used for any number of people which will handshake with each other, and this will be the total number of handshakes in that group of numbers. Okay, so thank you so much. This is the end, and this is one of the very interesting question of the combinatorial nature. So that's it for today, and I will see you with some more interesting questions in our upcoming videos. Thank you so much. Hello again, guys. So this is problem 51 of the second edition of Probability and Random Processes for Electrical Engineering by Alberto Leon-Garcia, and in this question we are told that a die is tossed twice, number of dots facing up is counted and noted in order of the occurrence. So let us find the value of probability of A such that B is given, and the value of the probability of B such that A has been given. Okay, so what are A and B? So A is the event of total number of dots is even, and B be the event both tosses had an even number of dots. Okay, so this is clearly the problem of the conditional probability, in which we are given any of the probabilities of the event and we have to find out the probability of the other event. Okay, so in these type of questions or in any probability related question, what are the steps? So I have told you that initially you have to write the sample space. Okay, so in our sample space here a die is tossed twice. So in sample space here, when a die is tossed twice, so what would be the elements of the sample space? So initially I can also get 1 1, I can get 1 2, okay, I can get 1 3. First toss is 1, the second toss I am getting 3 dots. Okay, 1 4, 1 5 and 1 6. Okay, so this is for the possibilities where only the first toss is having 1 dot facing up. Okay, similarly in our second row I can have 2 1, 2 2, 2 3, 2 4, 2 5 and 2 6. Okay, so this is about the events where the first toss will have the 2 as the dots facing up. Okay, similarly we can get them from here to 6 1, 6 2 up to 6 6. Okay, here these would be, okay, these would be my sample space. And how many elements would I have here? I will have 6 multiplied by 6, 36 elements here. Okay, so this is the sample space. So after it we have to write the elements which are in our set A. So what is set A? A basically is the event that the total number of dots is even. So what are the events here in which total number of dots are even? So let me write them here. So I can see that here 1 plus 1 is 2. So this is the first event. Similarly here 1 plus 3 is 4, 1 plus 5 is 6, which is the even number. 2 plus 2 is 4, 2 plus 4 is 6, this is 2 plus 6 is 8. Similarly 2 plus 6 is again 8, 6 plus 6 is 12. So these are all the even numbers which I can write here. So let me denote my event A with this red color. Okay, so let me denote it, or let me denote it with this blue color. So A is basically 1 1, okay, 1 3 and also 1 5. Okay, similarly I can have 2 2, 2 4 and 2 6. Similarly here, sorry, this is 3 1, 3 3 and 3 5. Okay, now 4 2, 4 4, 4 6. These are the events where the sum of both the tosses is even. Okay, similarly here 5 1, 5 3 and 5 5, and in the last one here we will have 6 2, 6 4 and 6 6. So these are the elements of my event A, in which the summation of each of the event is now even. So just like 1 plus 1 is 2, taking randomly here 4 plus 2 is 6, 5 plus 5 is 10. So all of these are basically the even numbers. Okay, similarly let me move up here and we have to see that what is the event B. So B is the event where both tosses had an even number of dots. So let me look at here that what are those events where both the tosses had an even number of dots. So this one here 2 2, 2 4, 2 6. Okay, similarly 6 2 and 6 6, these are also the two tosses where each and every one has the even number of tosses. So now writing it here, and let me denote it with this B. So B is now, let me write first one, that is 2 2, both are the even numbers, 2 4 both even, and 2 6 both are even again. Similarly 4 2, okay, 4 4 and 4 6 both are even. And now the last one are 6 2, 6 4 and 6 6. So this is the event B, this is event A, in which we have written all the elements. Okay, after it what you have to do, you have to find the probabilities of each of the event. Okay, so let me now move down and let me write here the probability of A and the probability of B. I have to calculate them again. So how to find out the probabilities? So to finding out the probability, we have to use the formula that the number of items in set A, okay, divided by the total number of elements in sample space. Okay. So in order to find the probability of A, what we have to do, we have to count the number of items in set A. So these are basically 1, 2, 3 and 1, 2, 3, 4, 5, 6. So we have total number of elements here are basically 18 and the total number of elements in the sample space are 36. So it would be 1 by 2 or 0.5. So the probability of event A is 0.5. Similarly, in order to find the probability of B, what we have to do, number of items or elements in set B divided by the total number of elements in sample space. Okay. So let me now count the number of elements here. So 1, 2, 3 and 3 multiplied by 3 are 9. Writing them here. So 9 divided by the elements in sample space are 36. So this would be 1 by 4 or 0.25. Okay. So these are the two probabilities which I have to find out. Now what is in the question? We are asked to find the probability of A given B and also probability of B given A. So let me use the formula here that the probability A given B. So from the conditional probability, I know that the probability of A given B is probability of A intersection B whole divided by the probability of B. Okay. Why is it? Because I have to write this probability as the event which has already been occurred. So B has already been occurred and I have to find out the value of the event A. So that's why I have to write this probability of B in the denominator. But what is the probability of A intersection B? So to find out the probability of A intersection B, what I have to do, I have to find out the set which is A intersection B. So what are the elements which are in both of A and B? So let me see here. So these are available in both of 2. Okay. 2, 4 is also here, 2, 6 is also here. Okay. So I can see that all the elements here are already in the set A. So the A intersection B is basically B. Okay. We can very easily verify here that this is also here. So now let me write the A intersection B is also B. Okay. So the probability of A intersection B, again the same formula, that the number of elements in the A intersection B divided by the total number of elements in the sample space. So as the number of elements in A intersection B are the same as that of the set B, so it would be 9 divided by 36 and it would be 0.25. Okay. So now we have also calculated it. Now putting their values here in this formula. So the probability of A given B is how much? The probability of intersection B is calculated and that is 0.25. So 0.25 and divided by the probability of B. So let me look for probability of B and that is again 0.25. So that is again 0.25. These two will cancel out and I will get here 1. So what does it mean? It says that whenever B will occur, there is 100% chance that A will occur too. Okay, with the occurrence of the B, there is a 100% chances that A will occur too, because B is the event that the board tosses has the even number of dots. Okay, so and A is the event that the summation of the dots is even, and we can very easily see that the summation of these two events is also even. So we can see that the occurrence of the event B also says that A has also been occurred. Okay, so that is the 100% chance of the occurrence of A when B has occurred. Similarly, in order to find the probability of B given A, that what is the probability of B when A has been occurred, so that would again be probability of A intersection B, while the event here has occurred is this A. So the probability of A will be here. Okay. Now writing their values, the probability of A intersection B is 0.25, while the probability of A is how much? Let me see, the probability of A is 0.5. So here I will get 1 by 2 or 0.5. So what does it mean? It means that 50% chance, while 1 means 100% chance. So 50% chance means that if A has occurred, there is 50% chance that B has occurred too, because you can very easily see that half the elements here in A are basically B. So whenever any event in A will occur, you can very easily see that there is a 50% chance that B has occurred as well. Okay. So that's it for today, in which we have discussed a very important problem related to the conditional probability, and with some more problems I will see you very soon. Thank you so much and take care of yourself. Welcome back, guys. So this is problem 52, and here we are asked that a number is selected at random in the interval -1 to 1. Okay, so we have two events here, event B and event C. Why are they not called event A or B? Because the same question we have solved previously, and the link of that question I will put in the description. Okay, so here we have two events where the event 1 is the modulus of x minus 1 by 2 is less than 1, while the event C has x greater than 3 by 4. So we have to find the probability of B given C and probability of C given B. Okay, so let me now again see that what was there. So there we had these lines. Okay, and here we had this 1, this -1. Okay, this is minus 0.5, this is 0.5 as well, and here we had basically two events. So event B, basically there was, okay, so event B, there was, I basically represented event B with this green color. It basically started from here and went from there to here. Okay, so this was what, this was the event B. Okay, similarly for event C, we had used the blue color, and it started from this point, where this point is 0.75, or 0.75 is also 3 by 4. It started from here, okay, and ended here. So here it was this event. So this was the event C. So we have also seen that the probability of B was how much? The probability of B was 1.5 divided by 2. So that was 1.5 divided by 2 was how much? It was 0.75. Okay, and the probability of C was 1 minus 0.75 divided by 2. So, this was what? 0.25 divided by 2. So, it was 0.125. Okay. How did we calculate it? What does it mean by this 2? So, 2 was what? 2 was basically this overall distance, okay, between this minus 1 and plus 1. This was 2. Okay. Similarly, here in B, the distance between these 2 points was how much? This was 1.25. So, the probability of B was calculated by dividing this 1.5 by this 2, okay, as I have done here. Similarly, here this was the event C and the distance here was 0.25. okay. So, again we have used it and divide it over this 2 as well. I have also explained it in my previous lecture, and the link of that lecture is already available in the description box. So, you can look at those explanations as well. Okay. So, now what we have to do, we have to find the probability of B given C and probability of C given B. So, what is here? We can see that in order to find the probability of B given C is always equal to the probability of B intersection C divided by the probability of C by the conditional probability. Okay, but we don't know the value of probability of B intersection C. So, the value of probability of B intersection is how much? Let me go towards here as well, and here we can see that the intersection between B and C is again this point. Okay, so that is the intersection where the both has been occurred. So, therefore, the value it has is 0.25. okay. So, in order to find the probability of B intersection C, what we have to do, we have to divide it over the overall distance, which is 2 here. So, again I will get here 0.125, which will remain same here. Okay. So, now in order to find the probability of B given C, the probability of B intersection is given, C is given. So, that is 0.125, while the probability of C is how much? That is already calculated, and that is also 0.125. So, writing 0.125, what I will get? I will get here 1. Okay. So, it says that if C has occurred, there is a 100% chance that B has already occurred, because we can very easily see here that here this event is also a part of my event C. So, whenever it occurs, it also occurs, because that is the subset of my event B. Okay. So, therefore, it basically satisfies what we can visually see here. Okay. Similarly, in order to find the probability of C given B, what we have to see again, probability of B intersection C and dividing it over the event which has already occurred. So, that is B. Okay. We have already found out the value of probability of intersection C, and that is 0.125. okay, and dividing it over probability of B. So, let me see that what is probability of B, and that was 0.75. So, that is 0.75. So, let me calculate it. So, calculating it, 0.125 divided by 0.75. okay. So, that is 1 over 6 or 0.167. So, 0.167. So, that is the probability of C given B. So, that is, there is a 16% chance that if B has occurred, that C and C will also occur in it. Okay. So, that is it for today. We have discussed another application of the conditional probability by using this line function, and this is basically a part of our previously done question, which was basically the question number 17 or so. So, we have also discussed it here. So, I hope you have understood it, and I will see you with some more interesting questions in our upcoming video. Thank you so much, and I will see you soon. Hello again. So this is the question 54 in the probability and random processes for electrical engineering, and this is the second edition of that book. In this question we are asked to find the probability that 2 or more students in a class of 20 students have the same probability. Okay, so in these type of questions you have to first of all see that what is the essence of these questions. So whenever you get the statement like that 2 or more students in a class, or 2 or more people, or 2 or more things, so first of all you have to see that what is meant by this. So 2 or more people has, the opposite of it is, basically that no one has. Okay, so if 2 or more people has, no one has, that is the opposite. And once you will find something that no one has, so from it you can again calculate all of these things by finding the complements. Okay, so first of all you have to get the essence that if 2 or more people in a class has something, so that is the possibility that all the people in the class, or all the students in the class, can have a birthday on the same date, or any number of students may have it on the same date. But if you have to find out the possibility that any 2 or more people have the birthday on the same date, you may find out that no one has the birthdays on the same day, and after complementing it you may find the answer. Okay, so let me start it from this statement that no student has a birthday, no 2 students, let me rephrase, no 2 students, 2 or more have birthday on same date. Okay, so let me write it, the probability of n of s, let me call it n of s, and for writing it what I have to do, I have to find out the total choices, okay, and then the desired choices. So to find the total choices here, let me call it equation A. So to find the, let me move here, and to find the total choices, what I have, that is basically the permutation problem in which I have NPR. So I have total choices of 365, and from these 365 I have 20 choices. So I want to find out that in these 365 days I should have 20 days which are apart from each other, and these 20 can have any sequence, and those sequences will be different from each other. Okay, so that will create NPR. Okay, so that is the desired choices. So now in order to find the total choices, what I can have, or what choices will I have? So again, considering the 20 slots here, okay, up to 20. So 1, 2, 3 up to 20. So for each of the student, any day can be of his birthday. So 365, 365, 365. So each student has 365 choices up to 20th student. So any student can have any choice, and that is the total choices, or the total number of the possible outcomes which I can have. So therefore it will be like 365 multiplied by 365 up to the 20th 365, and here I will have 365 into 20. Okay, so here we have these total choices. Now writing these values here, what I will get here, this is now 365 and the choices it has is 20 divided by the 365 whole square of 20. So now I have to find the probability of n of s. For it I am going to use the calculator, and here I have a function and that is the permutations. Okay, so that is written here NPR. So writing it here N365 and that P and the value of the choices I have is 20. So writing it this, so I will get these number of values. Okay, so this is basically very huge quantity. Now dividing it over this 365 into the 20, so 365 and the power it has is 20. So now I will get this 0.59 or 0.58. Let me write it 0.58. So the probability that no two or more students have a birthday on the same date is basically 0.58. Okay, so that is probability of n of s. Now the question here that is that the two or more students should have the same birthday. So what I have to do, I have found out the value here that no student have this birthday on the same date. So in order to find the complement here, what I have to do, I have to find the probability that SS. Okay, so that is basically 1 over probability of n of s. So now writing their values, I will get 0.58 and here how much would it be? 1 minus 0.58, so that is 0.42, that is 0.42. Okay, so this is the chance that this in a class of 20 students, 2 or more than 2 students will have a birthday on the same date. Okay, so that is the problem in which we have seen the notion that if you get any question like this one that which encounters many choices, so you have to do the rightful thing just by using this formula, which is a very useful formula for your understanding, that you may reduce the number of choices by first finding out the negative of that statement and then find the positive statement by finding the complement of that statement. Okay, so that's it for today, and I will see you with some more interesting question in our upcoming video. Thank you so much, and I will see you soon. Welcome back, guys. So this is probability and random variable, and this is question 71 of the book by Alberto Leon-Garcia, second edition. So here we are asked to find the probability that the block contains 3 or more errors, and the statement here we have is a block of 100 bits is transmitted over a binary communication or channel. Okay, so the channel we have here is this binary communication channel with the probability of error is 10 to the power minus 3. So here we have to find the probability that the block contains 3 or more errors. So more specifically, we can write here the solution such that we have here 100 bits. Okay, and these are transmitted over a binary communication channel, and the scenario, the channel has been model is like this one. This is the transmission end, and this is basically the reception end. Okay, so here we have this transmission end, and here 2 bits can be sent out here. One is here 0 and the other one here is 1. Okay, so if the bit is transmitted here from here to here, so here we can get 0 or can also get 1 here. Okay, either the bits transmitted from this transmitted end to this reception will either be 0 or 1, or if 0 is transmitted, it can either be 1 or 0 as well. Okay, so here this is the transmission end and this is the reception end or the receiving end. So here the probability with which we will get the error means if 0 is sent, we will receive 1, or 1 is sent, we will receive 0. So the probability of error is what? Let me write it here with this blue color. That is, let me call it P, and that is transform -3. Okay, and what is the probability that we will receive it correctly? That would be 1 minus P. Okay, so it will also be like this one, 1 minus P, and here it will be this P. So this is the overall scenario. Now 100 bits are sent here, and we want to find out that what is the probability that the block of 100 bits will contain 3 or more errors. I mean, if I am going to write here with this white color, so I want to find out the probability of the errors greater or equal to what? 3. Okay, so I want to find out the probability of errors greater or equal to 3. So it can also be written like 1 minus probability of the errors less than 3. So it will also be like this one. It can also be modeled like this one, like the summation of these two will be equivalent to 1. Let me write them here. The probability of errors greater or equal to 3 plus the probability of error less than 3, it will also be equal to 1. Okay, this is the overall scenario. This is the overall scenario, and it will be equal to what? It will be equal to 1. Okay, so now we want to find out the probability here, and we can see that here errors are basically, this is a binary communication, and we will either receive 0 or 1. Okay, 0 is for failure and 1 is for the success, or here success is the error and failure is no error. So here we have 100 trials, and out of these 100 trials we want to see that what is the chance that we will get 3 or greater than 3 successes. So this is clearly the binomial probability problem. Okay, and let me call this equation as equation A. So here in equation A we have two parts. One is this and the other one is this probability of errors less than 3. Okay, so what is this probability of error less than 3? Let me write it here. So the equation for the probability of errors less than 3 will be equal to the probability that the errors is equal to 0. Similarly, the probability that errors is 1, okay, and plus probability that the errors is equal to 2. So these are the three scenarios where we have error is less than what? Less than 3. Okay, here we have a scenario in which we can see that out of the n items, n number of items, we have 0 success, 1 success and 2 success. Okay, and the number of successes we can find out by using the binomial probability law as mentioned here. So what is basically the binomial probability law? Let me write it here. So according to the binomial probability law, in order to find the probability of the successes equal to the k, okay, what we can do, we can use here n choose k. Okay, what is n? N is basically the total number of the trials, and out of these trials we want k number of successes. Okay, and here the probability of the success is p with the power of k, and 1 minus p is the probability of this failure. So here we will get n minus k. Okay, so this is, let me call it the equation 1. So this is the equation we will be using in our question here. Okay, so this equation, putting this equation for all the types in B here. So this is, let me call equation B here, and let me write all the forms for it as well. Here we will see that the probability of errors less than 3, for probability of errors is 0 or success is 0, what we can get n0, okay, p0, and similarly here 1 minus p n minus 0. Similarly here, for this probability of errors equal to 1, this will be n choose 1, okay, probability 1 and 1 minus p, probability of n minus 1, and similarly for the two successes n choose 2, probability square and 1 minus p n minus 2, okay. So simply it can also be like probability of the errors less than 3, okay, starting it from 0 to 1 to 2, what we can do, we have to add them. So here it will be I will be from 0 to 2, okay, and here it will be n choose I, the probability of I, and 1 minus p, probability of n minus I, okay. So let me call it equation C, okay, and now putting C in A, okay. So putting C in A, what we can get here, probability of error greater or equal to 3 is 1 minus probability of error less than 3, so it will be equal to the, so this is what, this basically is the binomial probability law. Now putting values here, and for first expanding it, what I will get here, let me expand it first. So I will get here 1 minus, writing them here as well, it will be 1 minus n factorial divided by n minus 0 factorial and 0 factorial. So it will be n factorial divided by 0 factorial and minus 0 factorial, because whenever we will have here AB, and this AB is equal to the A factorial divided by B factorial or A minus B whole factorial. Using this thing here, what we can do here as well, this is the expansion of this and multiplying it with this P0, 1 minus P n minus 0. Similarly here, n factorial divided by 1 factorial and n minus 1 factorial, and this is p1, 1 minus p n minus 1, and here this will be n factorial divided by 2 factorial multiplied by n minus 2 whole factorial, and it will be p square 1 minus p n minus 2, okay. So now here it will be this thing, and here what we have to do according to this question, what we are going to write here, let me write here n equal to 100, because this is the total number of bits here, and p is equal to 10 as power minus 3, okay. So writing these values here, what I will get, so this is basically the solution which we were working to find out, and this is the expression for the bit error which we were aiming for. So that's it for today, in which we have discussed the number of the errors out of some block of bits. So this is clearly the binomial probability theorem, and here we have discussed many assumptions and also shown you this very popular formula that if you want to find out the probability of some larger quantity, you can find out the lower quantity and then subtract it out of 1 to get the larger subset of it, okay. So this equation A is one of the important aspect of this question, and I will see you with some more interesting questions like this one. Hello all. So this is question number 72 in our book of Probability and Random Processes for Electrical Engineering by Alberto Leon-Garcia, and in this question we are told that 10% of an item from a certain production line is defective. Okay, so 10% of the items is defective. Here we can see that this is that 10% items. What is the probability that there is more than one defective item in a batch of n items? Okay, so here in this solution, let me solve it. So we have the n items, okay, n number of items, and here we know that 10% of n items are defective. Okay, so what is basically the probability of the defective items? So the probability of the defective items is how much? That is 0.1. okay, so this is the probability of the defective items. Here what do I have to find out? I have to find out what is the probability that there is more than one defective item in a batch of an item. So I want to find out the probability that I have the number of items. Let me write the number of items as k, okay, where k is the number of defective items. Okay, so I want to find out that what is the probability that more than one defective item is in a batch of n. So we have to find out that probability that k is greater than 1. okay, so it can also be found out by using 1 minus probability that the number of defective items is less than or equal to 1. okay, so this is the same formula which we have previously seen. So this is the equation A. What do I have to find out? I have to find out this probability of k less than equal to 1. So let me first find it out. So the probability that the defective items is less than or equal to 1 is what? This would be the probability of the defective items is 0, or the probability that the defective items is equal to 1. okay, so this is another aspect of looking at it. okay, how can we find it out? It is very easy to find it out by using what? By using the binomial probability law. So according to the binomial probability law, what do I have to use here? I have to use the n number of items, and out of those number of items I want to find out the probability that 0 number of items is defective, and the probability of the defective items, which is 0.1, with what? With the power 0. okay, and the probability of 1 minus 0.1, this would be n minus 0. Similarly, for the probability that k is equal to 1, I would have n1, okay, 0.1 with this 1 power, and 1 minus 0.1 n minus 1. okay, so this is the equation. So here, solving it now, this would what? This is 1, because n factorial divided by 0 factorial into n minus 0 factorial. okay, so this will also be 1 multiplied by this would be 1 minus 0.1 is 0.9 with the power of n. okay, so here we can also see that it would be n factorial divided by 1 factorial and n minus 1 factorial, this, and here it would be 0.1. okay, and here 1 minus 0.1 is 0.9 to the power n minus 1. okay, here we can very easily see that this will be cancelled out with this one. okay, and here writing them, I will get 0.9 n. okay, similarly here it would be n minus 1 factorial divided by the n minus 1 factorial. okay, and multiplied by 0.1 into 0.9 n, and multiplying it with 0.9 minus 1. So now here we can again see that this will be cancelled out with this one, and here these things or these terms will remain here. Okay, so I will get here 0.9n plus this will be 0.9n and here 0.1 and it will be 0.9. So 0.1 divided by the 0.9. Okay, now let me move further here. Okay, so here it will be taking this 0.9 common from it, it will be here, and I will get here 1 plus this is 0.1 divided by 0.9. So how much it would be? Okay, here I also have this n as well. So here because this n is here, so I will get here n divided by 9. Okay, so this is the solution for the probability that k is less than or equal to 1. Okay, so let me call it equation B. Now putting equation B in equation 1, what I will get? I will get the probability that k is greater than 1 is equal to the 1 minus 0.9 n 1 plus n by 9. Okay, so what is this? This is basically the answer which I wanted to find out for the question that what is the probability that the n number of items out of what is the probability that more than one items in the batch of n items is defective. Okay, so let me see the statement here as well. So this is the statement and the question we have solved have the answer written here. Okay, so that's it for today, in which we have solved this question, and I will see you with some more questions in our upcoming video. Till then, take care of yourself and I will see you soon. Welcome back, guys. This is question 75 in our book, and here we have the statement that a system contains 10 chips. Okay, so the number of the chips we have is 10. The lifetime of each chip has an exponential probability law with parameter alpha. Find the probability that at least half of the chips are functioning after 1 by alpha seconds. Okay, so this is the statement, and now let me find the solution of our problem. Okay, so the number of chips we have here 10, this is the given data, and the lifetime of each chip has an exponential probability. Okay, so the probability of the lifetime is what? It is following this exponential probability law with the parameter alpha. So I have here this minus alpha t because it is following what? The exponential probability law, and here according to this law what will happen, it also is showing me the probability distribution if it is t with this initial value equal to 1, and what will happen? It will decay slowly, and therefore it is what? This is the exponential of minus alpha t. Okay, so it is also being shown here, and this is this probability. Okay, so now we have to find the probability that at least half of the chips are functioning. So what is the value of the half chips? So that is probability that functioning chips are at least half, so it should be greater or equal to 5 because 5 is the half of this 10. So I want to find out this probability, and from it after what? After 1 by alpha seconds. Okay, so the probability of lifetime after 1 by alpha seconds, it would be how much? So lifetime after 1 by alpha seconds, how much would it be? So it will be just minus alpha, and writing the value of t here 1 by alpha, because now t is equal to 1 by alpha. Okay, so writing it here, these two will cancel out, and here we will get exponential of minus alpha. So this is the probability of the lifetime after 1 by alpha seconds. So this is the probability. So now in order to find the probability that functioning is greater or equal to 5, okay, functioning chips are greater or equal to 5, what it would be? It would be the probability that functioning are equal to 5, or probability that functioning chips are equal to 6 up to the probability that functioning chips is equal to 10. Okay, so these are all the values which I want to find out, and this is basically that's it. Okay, so now in order to write the values here, what I would have to do, I will have to use the binomial probability law. Okay, so according to the binomial probability law here, let me use the color this white here as well. So here what would be, I will have n 5 and the probability of the lifetime is exponential of -1 with the power 5 here for this 5, and here 1 minus exponential of -1 and n minus 5. Okay, similarly for the 6 here, n 6, okay, exponential of -1 with 6, and this 1 minus exponential of -1 and -6, okay, and so on up to and until I will get here n 10, okay, and exponential of -1 this 10, and 1 minus exponential of -10, sorry, -1, and this is n minus 10. Okay, so here let me put the value n equal to 10. Okay, putting the values of n equal to 10 here, here, and here. Okay, so what I will get, I will get this probability of the functioning is greater or equal to 5. So I have calculated it and I will get 0.289. Okay, so this is just by putting here, calculating all the values, what I will get here, I will get this value, and this is what, this is the answer which I wanted to find out here. Okay, so this is all the conceptual procedure which I had to follow in order to find the solution. So this is the statement, and these are all the steps which I had to use here in order to find the solution of my question here. Okay, so that's it for today, in which I have solved this question. If you have any question regarding it, please ask me in the comment box. I will see you with some more interesting questions and more exercise problems in our upcoming video. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So this is problem 76 of our book, and here the statement is machine makes error in a certain operation with probability p. Okay, so the probability of error is p. There are two types of errors. The fraction of errors that are type 1 is alpha. Okay, so type 1 error, and we have type 2 errors, and the fraction of the type 1 error is alpha, while the fraction of the type 2 error is 1 minus alpha. So before proceeding to the other parts of this question, let me first write the given data, okay, to formulate the strategy for solving this question. So here we have probability of error, that would be p. Okay, and from this statement we can very clearly infer that the probability of no error would be how much? That would be 1 minus p. Okay, similarly for type 1 type of data, we have the fraction of it equal to alpha. Okay, for type 1 error we have the fraction of it alpha, and for type 2 we have 1 minus alpha. So in order to find the probability of it, we have to multiply this fraction with the total probability, and we will get the probability of that type of error. So for type 1 error, what we have to do, I have to multiply alpha with p probability, and for type 2 I have to multiply the fraction of it, which is 1 minus alpha, with the probability of error. Okay, so this is all the data which we had in the statement. So now let us proceed towards the solution of our question. So now for it, let me move down here So we have to find out that what is the probability of k errors in an operation. Okay, so this is the first statement or first part of our question. So here we have A, and here we have to find out the probability of k errors in n operations. So this is clearly the problem of the word binomial probability law, and here the formula of it would be n choose k. Okay, from n we have to find the probability of k errors, and the probability of the error is how much, that is p. So the power of it will be k, and similarly the probability of no error is 1 minus p, and the power of it will be n minus k, and this is what, this is because of the binomial probability law. Okay, what is part B? So in part B, what is the probability of k1 type 1 errors in n operations? This is part B here. So for solving it, let me move down further. Okay, so this is part B, and we have to find the probability of k1 errors in n operations. Okay, so here we have the total number of operations equal to n, while the trials we have is k1. Okay, and the probability of k1 type error is here. So I have to write here alpha p, and with it I have to write this k1, and the probability that we don't have the type 1 error, that would be 1 minus alpha p, and here we will have n minus k1. Okay, similarly now for part C, we have to find out what is the probability that k2 type 2 errors in an operation. Okay, so here we have to, let me move down further. Okay, so in C I will have to find out that what is the probability of k2 type 2 errors in n operations. Okay, so here it would be what, n k2. Okay, and the probability of type 2, so this is this one, the probability of it is given, and it would be 1 minus alpha p. Okay, and the power of it is k2, and the probability that it is not the type 2 error, that would be 1 minus alpha p. Okay, and the power it will have would be n minus k2. So this is the solution of part C. Similarly in part D, we have to find out what is the joint probability of k1, okay, k2 type 1 and type 2 errors respectively in n operation. So here in last part of it, what we have to do, we have to find the joint probability of our problem. So here it would be the probability of k1 k2 in n operations. Okay, we have to find the probability of k1 k2 errors. So this, there we have two categories which are k1 k2. Okay, and the third category here as well, these are two categories of the error. Okay, and also we have third category that we will have no error. Okay, and we also know the probability of the no error, and that is 1 minus p. Okay, so now writing all these terms here and finding the probability here, and the problem here will become the problem of the multinomial probability. Okay, so for the multinomial probability, we have the total number of operations n, and taking the n factorial, the first problem we have is this k1, so writing the k1 factorial. Similarly k2 types, so k2 factorial, and I have another type of the things which are of no error, so it would be k1, let me write it here, k1 and k2, these two are the errors. Okay, so the terms which are left will be of no error, and how to find it? So why we have to subtract this term, these terms from the n, so from it I will get n minus k1 plus k2. Okay, so these will be the terms of with no error. Okay, so here similarly writing here the n minus k1 plus k2, and the factorial of it. Okay, so this is here. After it, we have to multiply the probability of all these terms. So the probability of k1 is how much? That is alpha p, and writing the power of it k1. Similarly, the probability of k2 is 1 minus alpha with p, and the power of it is k2. And similarly, the probability of no error, as we previously found out, is how much? Let me write it here. That would be 1 minus p, and the power of it will be n minus k1 plus k2. Okay, so this will be the power of it. So this is the solution which we in which we have to find out the joint probabilities of k1 and k2 terms in our n number of trials. Okay, so that's it for today, in which we have found out all the terms related to our question 76. And if you have any question, you can ask me in the comment box. I will see you with some more questions in our upcoming video. Till then, take care of yourself, and I will see you soon. Hello guys, so today we are going to solve the problem 2.77, in which we are given this diagram. Here we have some inputs and some outputs, and here this is basically the communication channel. Okay, so this problem is basically related to the communication channel and how probability is used in the communication channel to find out different probability. And the main thing we actually are going to use here is basically the Bayes theorem. Okay, so we are going to discuss the Bayes theorem, that how it can be used to find out different probabilities. So a non-symmetric binary communication channel is shown in figure 2.3. Assume the input is 0 with the probability p. Okay, so the probability of input equal to 0, that is p. Okay, and the probability of the input equal to 1 is 1 minus p. Okay, as given here. Okay, this is given here and also here as well. So what we have to do in part A of our question, we have to find the probability that the output is 0. So we have to find the probability of 0. Okay, so we have to find the probability that the output is 0. Okay, so why did I have you use this red color here? So here we are going to use outputs with this red color, while this inputs will be used with this blue color as well. Okay, so we have to find the probability of output equal to 0. Okay, so which theorem are we going to use here? So here, in order to find the output equal to 0, we are going to use the theorem on total probability. Okay, so what is the theorem on total probability? We can see here that here we have this output 0, and this output 0 has been caused by different inputs. If either we will have 0 at the input, or we can also have 1 at the input, and from these two possibilities we can get this output here. Okay, so in order to calculate the probability of 0 here, what we can do? So the probability, this is part A, the probability that output is 0. Okay, so there are basically two possibilities for it. First possibility is the probability of the output equal to 0 given that input is 0. Okay, if input is 0, then what is the probability of 0? And similarly, what is, multiply it with the probability that, what is the probability that input is 0. Okay, so this is one of the possibilities that we have. What is the probability that output is 0 given the input is 0, but what is the actual probability of input equal to 0. Okay, so we have calculated it, or there is another possibility here as well, and that is the probability that output is 0, okay, given that input is 1. Okay, so what is this case? This case is basically the erroneous case where we are having this link. Okay, so this link is basically showing me this case, while this link here is basically of this case. Okay, this overall case, I mean, while this one here, the probability of input equal to 1, we have also have to find, multiply it with the probability that input is equal to 1. Okay, so what is this overall case basically portray as this possibility. So now, do we have all these values? Yes, we have all these values. So let me put them here. So the probability of output equal to 0 such that input equal to 0, this is this case. Okay, so the probability of it is 1 minus epsilon 1. Okay, and what is the probability of input equal to 0? I have already told you guys the probability of it is already given here, and that is p. Okay, similarly, what is the probability of output equal to 0 given that input equal to 1? What is this? This is this one, okay, this error, and the probability of it is epsilon 2, while the probability of input equal to 1 is this one. Okay, and that is multiplied by 1 minus p. Okay, so that is what, so that is basically the probability of output equal to probability of the output equal to 0. Okay, so that is the solution, and you can simplify it some more, but the answer here is this one. And if you know the value of E1, E2 and P, we can very easily put them here and find out the value of probability equal to 0. So that is due to this theorem, which is called the probability theorem on total probability, which is given here. Okay, so that is for the part A of my question. In part B of my question, I have to find out that if I have received 1 here, what is the probability that the input given here was 0? Similarly, if I also received 1 here, what was the probability that I have received 0 here? Okay, I have received 1 here, I mean there was no error. So for it, I have to use the Bayes theorem, okay, in which the final event has been occurred, and I have to see the cause of that effect. Okay, so what I have to do, I have to find the probability that, what is the probability that input is 0, okay, given that the output is what? Let me have a look here. Given that the output is 1. Okay, so output is 1. I have to find out this probability. So in order to find this probability, I have a Bayes theorem in which I have to write that the probability of output equal to 1 given that the input is 0, okay, and multiply it with the term that what is the probability of input equal to 0. So I have to write here probability of input equal to 0, okay, and divide it over what? Divide it over this term, that what is the probability of output equal to 1. Okay, so the probability of output equal to 1. Okay, so again I have to use the theorem on total probability over 8, theorem on total probability. Okay, so now let me put their values here, and by putting their values I will see that the probability of output equal to 1 such that input is equal to 0. What is that? Output is equal to 1 such that the input is 0, that is E1, okay, multiplied by probability of input equal to 0. What is that? That is here, that is P. Okay, so multiplying it with P and dividing it over this term, where this will be probability of output equal to 1 such that input is equal to 1, and multiply it with the probability of input equal to 1, okay, and adding it with the probability such that output is equal to 1 such that input is 0, okay, and multiplying it with what? Probability of input equal to 0. So by putting their values, I will see that I will get the value of this term, which is now here. Okay, so now let me put their values here. So putting their values here, what I will get, this would be E1 into P, and the probability that output is 1 such that input is also 1. Okay, this one, that is 1 minus E2, that would be 1 minus E2, and multiplying it with the probability that input equal to 1, and what is that? That is 1 minus P. 1 minus P, okay, and the probability of output equal to 1 such that input is equal to 0. This is this one, output is 1 such that input equal to 0. So that is how much? That is E1. Putting value here, E1, and multiply it with the probabilities that input equal to 0, and that is P. Okay, so that is the answer, that what is the probability of input equal to 0 such that output equal to 1. That is the answer of part B. Okay, similarly here you also have to find the probability that the input is 1 given that the output is also 1. So you have to find the probability that once you have received this output equal to 1, okay, once you have received the output equal to 1, which is, what is the probability that input equal to 1 such that you have already received the output which is already 1. So you have to find its probability. Okay, so it is again calculated by using the Bayes theorem, and you will see that by putting their values you will see that which is more probable as compared to the other if you have the values of P, epsilon 1 and epsilon 2. So it will show you the feasibility of this communication channel. Okay, it will show you the feasibility of this communication channel which we have here, that is the communication channel with parameters epsilon 1 and epsilon 2. Okay, so that's it for today, in which we have discussed a very important topic of the bit probability estimation from the channel parameters, and we have seen that how to calculate the possible bit at the input if certain output has been received and vice versa. So we have used two theorems. The first one is the theorem on total probability, while the second one here is the Bayes theorem. Okay, so that's it for today, and I will see you with some more interesting questions which are related to the probability and random variables. Till then, take care of yourself, and I will see you soon. Welcome back, guys. So this is question 2.103 of the third edition of our book, and here we are asked that 3 types of packets arrive at a router. Okay, so we have a router, and to this router we have 3 type of packets which arrive. Okay, so 10% of packets are expedited forwarding. Okay, 30% are assured forwarding and 60% are best effort, okay, which are represented by BE. So according to this information, what do I have to find out? There are different parts of it. So I have to find out the answer of part A, part B, part C. So before proceeding to find the answers of each part, let me first write down the data which we have. So expedited forwarding is 10%. 10% of the packets are expedited forwarding. Similarly, assured forwarding is 30%, that is AF. Okay, so here we have this 30%, and BE or best forwarding or best effort, best effort is 60%. Okay, so according to this data, we can also find out the probabilities of each of them, and the probability of EF is how much? That is 0.1. Okay, similarly, the probability of AF is 0.3, and the probability of BE is how much? That is 0.6. Okay, similarly, on the basis of this data as well, what we can also find out, we can find out the probability that no expedited forwarding is 1 minus 0.1, so that would be 0.9. okay, probability of no assured forwarding NAF is 1 minus 0.3, so it would be 0.7, and probability of no best effort, that would be 1 minus 0.6, so that would be 0.4. okay, so now we have this given data, and on the basis of this given data, what we have to find out, let us talk about the part A of this question. And here we have to find the probability that K of n packets are not expedited forwarding. Okay, so we have n number of packets, total number of packets are n, and out of these n packets, K should not be expedited forwarding. So it is clearly the binomial probability law. Okay, and we can very easily find out the probability that K out of n packets are not expedited forwarded, because here we also have no expedited forwarding, we have expedited forwarding, we have all the probabilities, and on the basis of it we can find out what the probability of the K out of n are no expedited forwarding. So it would be what? It would be total n from n out of K are not expedited forwarding, and the probability of NEF, whether the power is K, and the 1 minus probability of NEF, okay, and the power of it will be n minus K. Let me put their values here, and here it will be n choose K, and the probability of NEF, or here it is given also, so here it would be 0.9 K, and 1 minus 0.9 K is 0.1, and it would be n minus K. Okay, so this is the probability of K out of n are not expedited forwarding. Okay, so this is the answer of our question, part A. Okay, so this is the answer of part A of our question. Similarly, in part B, suppose that packets arrive one at a time. Okay, each packet is arriving one at a time, so we have to find the probability that K packets are received before an expedited forwarding packet arrives. Okay, so before the arrival of the expedited forwarding, we have received how many packets? K packets are received, and after these K packets, we have received this expedited forwarding. We also have the probability of the expedited forwarding here as well, and no expedited forwarding here as well. So let me solve it, and for it let me move down somehow. Okay, so part B here, the probability of k packets reception before okay EF received. So this is what? This is clearly the problem of the geometric probability law. This is the geometric probability law, where the success is the reception of this EF packet. Okay, so until and unless this EF is not received, this can be written as the probability of what? So here probability of no EF, and it should be k, because after k packets, what will we receive? We will receive this expedited forwarding. Okay, so this will be here. So now let me put their values here, and after putting their values, what I will get? I will get 0.9 k multiplied by 0.1. Okay, so this is what? This is the answer of this question as well. Okay, so this is the answer of part B. Similarly, now part C here, find the probability that out of 20 packets, 4 are EF packets, 6 are AF packets, and 10 are BE packets. Okay, so out of 20 packets, so let me write the data here. Okay, so let me write this data here. So total number of packets are 20. Okay, so from these, out of these packets, the number of expedited forwarding are how much? Let me see them. These are, you can see that these are how much? These are 4, expedited are 4, AF are 6, and 10 are BE. Okay, so these are here 4, number of AF are 6, and number of BE are 10. Okay, so on the basis of this data, what we can find out here, we can also find out the probability of expedited forwarding, and that would be 4 divided by 20, and here it would be 1 over 5 or 0.2. Similarly, the probability of AF is 6 divided by 20, or this would be 3 divided by 10 or 0.3, and here the probability of BE would be 10 divided by 20 or 0.5. These are different probabilities. Okay, so we have found them out, and clearly this is the question of what? This is the question of multinomial probability. Okay, so this is the question of multinomial probability, and according to the given data, we have to find out the probability of 4 EF, okay, 6 AF, and 10 BE out of 20. Okay, so here, according to the multinomial probability law, I have to take the factorial of the total number of the packets and divide it by the number of packets of the first class multiplied by the number of packets, factorial of the number of packets of second class multiplied by this last class, and I have to multiply them with the probabilities of each class. So, the probability of EF is given here, that is 0.2, and with it the power of it will be the number of elements in that class. Okay, this is now this 4, and also here this 4, let me write them here, this is 4 and this is here as well 4. Okay. Similarly, now the probability of the elements here, this would be 0.3, that is AF, and the number of elements here are 6, and also the probability of B is 0.5. So, writing it here, and the power it has is 10, which is also given here. Okay. So, after finding out all the combinations and all the things here, we will get the answer. So, the answer of it will be calculated by using the calculator. So, if you have found out this expression, it is also enough, and we can conclude that you have reached to the solution of this problem. Okay. So, that is it for today, in which we have discussed the probability scenario of the packets which are arriving towards or to the input of any router port. Okay. So, that is it for today, in which we have discussed a very simplified scenario in a very interesting manner, and I will talk more about the same kind of problems in our upcoming video. Till then, take care of yourself, and I will see you soon.